Oh, yeah, yes, thank you. Okay, so thank you very much for a nice introduction. And first of all, I'd like to thank the organizers for inviting me in this workshop. And actually, this is the first trip to Europe after the pandemic. And it's very nice to see you, my friends in Europe in person. Okay, so my name is Ryotaro Arita from University of Tokyo and Riken. And today I'm going to tell you about first principles calculation on LaH10, one of the prototypical systems of high TC high drive. And especially, I'm going to focus on the crystal structure and superconducting TC in this talk. And okay, so this work was done in collaboration with people in Tokyo and Rome and Keio University, Okayama University, Saitama, and Tohoku. Yes, but especially the key players are these young people, Yuta Watanabe, and that's one graduate student of my group, and Jose Flores Rivas from Rome. And these are references of my talk today. Okay, so so in this workshop, there are already many talks on superconductivity in LaH10, and I'm not going will not discuss too details about that. But anyway, in 2019, there are two experimental reports and from the group of Professor Hemre and Professor Helmet. And they concluded that they observed superconductivity. And so if we apply pressure as high as 150 gigapascal, and then transition temperature is about 250 gigapascal. And so in the first part of my talk, I'm going to discuss the crystal structure of this system. And as I will discuss in the next slide, actually the crystal structure of the system is very important to understand bearing instability in the system. And especially, I'm going to discuss in the phase diagram in the plane of temperature and pressure, in which region crystal structure, which is good for superconductivity, is realized. So this is the issue which I'm going to address in the first part of my talk. And so I'm going to start with this paper. So Ion area. And actually, I'm the co-author of this paper, and there are several co-authors in the audience. So in this paper, it's shown that so the density electronic structure or crystal structure is very important to understand the high TC superconductivity in the system. So if we look at the density of states of this high symmetric structure of FM3 by M, so we see that there is a very sharp peak around the film level. So this is good for superconductivity because superconductivity is in general an instability of film level. So the density of states of film level is very high. It's good for superconductivity. But if this the structure has some distortion, then this peak disappears, and so this is not good for superconductivity. And so if we plot the enthalpy as a function of pressure, and we see that this high symmetric structure which is good for superconductivity, becomes stable only for pressure as high as 300 gigapascal. So this is not apparently consistent with the experiment because in the experiment, high TC superconductivity is observed even around 150 gigapascal. So then in this paper, so we considered the effect of quantum effect, the effect of zero-point motion. And but here there is one more interesting property in this system because so if we calculate the phonon dispersions based on the harmonic approximation, then we see that at 150 gigapascal or 200 gigapascal, there are so many negative modes. So harmonic approximation is not good for this system. And so then in this paper, also we consider the effect of anharmonicity based on the self-consistent phonon theory, SCPT. And then so the system becomes dynamically stable. And based on this calculation, if we consider that the effect of zero-point motion, then can show that this high symmetric structure, which is good for superconductivity, can be stable even at 150 gigapascal. So due to the effect of quantum effect. So this is the calculation for zero temperature. And then my student, Yuta Watanabe, then he interested in the effect of finite temperature. And so he recently performed the path integral molecular dynamics simulation. And for the method of path integral molecular dynamics on Wednesday, maybe the Professor Hemler already gave an introduction to this method, so I'm not going to the details, but the basic idea of basic path integral molecular dynamics is the following. So namely, so we start with this Hamiltonian and we calculate the partition function and then do the Suzuki-Trota decomposition. And then, so here we see that if we prepare the PB replica, PB means the number of replicas copies, and for each atom, and if we perform the molecular dynamics simulation, then we can take account of the quantum effect. And in this formalism, so this PB, the number of copy or replicas, represents how quantum the system is. And so this mapping converges to give the exact quantum mechanical results in the limit of large PB. And so this is the plot of free energy as a function of PB. And the PB equal 1, this corresponds to the classical molecular dynamics. So by doing this calculation, we can think about the effect of finite temperature. And we see that if we, so PB is as large as 36, then the result is almost converged. So hereafter, I'm going to show the results of PB equal 36. And in this calculation, both finite temperature and the quantum effects are considered. And from the MD simulation, we look at the crystal structure for given pressure temperature. And these are typical examples. So in this case, it is symmetric, so no distortion. But when the temperature it's not high or pressure is not high, then the cage is distorted. And by looking at this structure and calculating the X-ray diffraction pattern, we discuss the symmetry of the system. So, okay, so let us start with the result of classical MD. And so in this calculation, quantum effect is not included, just final temperature effect. And here I'm showing two representative results. So at 200 Kelvin and 125 gigapascal, so pressure is low and temperature is low. So in this case, if we calculate X-ray diffraction pattern, then the cage is distorted and we see many subpeaks. But when the temperature becomes high and the pressure becomes high, and then the structure becomes symmetric and the subpeak disappears. And so we performed calculation for these 5 points. And we have seen that for the temperature was 300 Kelvin, then the structure is symmetric. But for these 3 points, the cage has some distortion. Right? So from classical MD, this result suggests there is some phase boundary here. And at 300 Kelvin, so if we apply pressure as high as 125 gigapascal, then the symmetric structure is stable. And then, so we move on to the PIMD calculation. And so this is the result of X-ray diffraction pattern. And we see that, so in all cases, there are no subpeaks. So apparently it seems that in those 4 points, the system has a cubic symmetry. But if we look at this point more carefully and do a space group analysis using PyMatogen, so there is a package to do a space group analysis. So there is a one parameter called simplex. Simplex means the measure how strictly we justify or determine the symmetry of the system. So when this number is small, then a small deviation from the ideal structure is detected. And for these 3 cases, the results are always FM3 by M. So the crystal structure is always symmetric. But for this point, when this parameter becomes small, then we see some deviation from the ideal structure. That means this point is on the border between symmetric phase and the low symmetric structure. So from this result, we can say that at 200 Kelvin, for which is high superconductivity, maybe both temperature effect and the quantum effects are important to stabilize the symmetry. But for 300 Kelvin, and when the pressure is higher than 125 gigapascal, only final temperature can stabilize the symmetric structure. And actually, recently, so Kevin, postdoc in the group of Professor Separate, contacted us, and he also performed similar calculation and uploaded the preprint in archive. And so in our calculation, so we do the so-called ab initio MD, and the unit cell is small, but he uses the so-called machine learning potential, and the system size is larger. And so the phase boundary is a bit different, but the basic message, I think, consistent with our calculation. So in this region, both quantum effect and the temperature effect can be reported. Okay, so this is a discussion on crystal structure. And then let us move on to the calculation of superconducting. Okay, so it's already discussed in many talks in this workshop. So superconducting TC can be calculated by solving this Eliashberg equations. And one problem is that, okay, so this delta is a gap function, and this VPH is a phonon-mediated attractive interaction, and this VC is a screened Coulomb repulsion, and this is a Green's function. And one problem of when we solve this gap equation is that the energy scales of these two interactions are very different. Namely, the attractive interaction is finite only for states in the vicinity of the film level, but the squeezed Coulomb interaction works for states in wider energy scale as large as the film bandwidth. And this mu is the squeezed Coulomb interaction, and we try to solve this equation at low temperature to cover the energy scales of the bandwidth. We have to introduce many Matsubara frequencies. So that is the problem. And so usually we introduce this empirical parameter mu star. But as was discussed in several talks in this workshop, so here we have some not well-defined factor, and this introduces some substantial uncertainty in the calculation of TC. And to overcome this problem, one approach is, of course, SCDFT, formulated by the group of Professor Hardy-Gross. And here we solve the so-called Kohn-Sham-Bogoliubov equations, and from here we can derive a gap equation. Yeah, and so actually the numerical cost to solve this gap equation is much easier, much cheaper than that of Eliashberg equation, because in the gap equation in SCDFT, we don't have omega dependence. So this is one advantage. And also can say it should be noted that we don't have to introduce mu star. So retardation effect can be discussed from first principles in this framework. But here it is very nice if we can solve this Eliashberg equation with a cheaper numerical cost. And recently, we formulated such a scheme based on the intermediate representation of the Green's function proposed by Shinaoka and others. So the basic idea of the intermediate representation of Green's function is the following. So we start with the spectral representation of the Green's function here. And so this is kernel, and we do a singular value decomposition for this K. And we introduce these basic. And Shinaoka and others, so they found that if we expand the Green's function in terms of U or V, then the number of bases can be as small as 30 or 40. And if we introduce a 30 or 40 bases, then Green's function, tau dependence or omega dependence can be reproduced very accurately. And if we use this, then actually we can solve this Eliashberg equation, because if we look at this equation, we see that it is a convolution of interaction and Green's function. So if we do a Fourier transform and go to a tau space, and then we can calculate the right-hand side of this equation. So the point is how to do a Fourier transform efficiently. And if we use an intermediate representation, we can do that very efficiently because so g over I omega or g of tau can be expanded in terms of this u. And so this u can be pre-computed and stored in the library. So once we calculate it, so we don't have to change it. So just keep it. And then so for example, in the case of this, we try to do, we determine the coefficient of the Green function. And then once we have this coefficient, then using this, we can calculate g of tau. So the calculation from g of tau or from g over I omega to g of tau or vice versa, from g of I omega to g of tau can be done very effectively. And then using this fact, then actually we can solve this equation very efficiently. And yes, so this is one demonstration. So here we calculate the eigenvalue of this Eliashberg equation, and this maximum eigenvalue, when this maximum value becomes unit 1, then that temperature corresponds to the transition temperature. And if we do the standard calculation, so I'm showing 2 examples for lanthanum LaH10 and niobium, elemental niobium. So the TC of elemental niobium is about 10 Kelvin, so it's quite low. So we need to introduce many Matsubara frequencies. So 4,000 is not enough. Okay. And but in the case of hydride, fortunately, TC is high. So if we introduce 1,000, 2,000 Matsubara frequency, then it's converged. But the numerical cost is still very high. And we do the same calculation using intermediate representation of the Green's function. And in this case, sorry, so this lambda is this cutoff. Yeah. And even though lambda becomes large, actually the Lmax, the number of bases required to represent the Green's function, is always 30 or 40. And we see that so the result doesn't change. And so with a very small numerical cost, we can solve this Matsubara frequency, Eliashberg equation. And so we implemented this scheme, and so we solved this Eliashberg equation. And yeah, so for the spin-coulomb interactions, we use the code LaH10. LaH10 is developed by my old friend Kazuma Nakamura in Kyushu Institute of Technology. And so this calculates the spin-coulomb interaction with random phase approximation. And this code can also calculate, estimate the Hubbard U or Hunt coupling using constraint RPA method. So when we derive an Hubbard U in the Hubbard model, we have to exclude the screening of low energy electrons, and this code can do such a constraint. But in this case, we don't have to introduce such constraint, and the calculation is a simple RPA. And for the spin-coulomb interaction, we use this. And in the following calculation, we neglected the omega event, so we use the static approximation. And the following part, so we use the quantum espresso, And Takashi Koretsune and LaH10 so they developed the code to solve this equation using IR basis. And the advantage of this approach is that we can solve the Eliashberg equation self-consistently. Self-consistent means that so in this Eliashberg equation, this is the Green's function, and the Green's function has a self-energy, and we consider the self-energy to the electron-hole coupling. And we solve this equation self-consistently, and we use this sigma in this Green's function. Yeah. And this self-consistency is sometimes very important because so this is a result of hydrogen sulfide, and we do a one-shot calculation. Namely, so if we calculate the self-energy in a one-shot calculation, starting with a non-interacting Green's function, then TC is a bit underestimated. And if we do a self-consistent calculation, then TC becomes closer to the experimental value. Yeah, but anyway, if we use an intermediate representation of the Green's function, then so the numerical cost to solve this Eliashberg equation becomes numerically very cheap. Yeah, but let me mention that this calculation is still expensive for how to say low TC superconductors, because we have in the case of low TC superconductors, another problem appears, namely, so we have to introduce the dense K mesh. And so this is a calculation of a niobium, and we see that so in the, as a function of the number of K points, we see some deviation, oscillation still. And LaH10, so he extrapolated this data and determined TC. But this strategy does not work with superconductor having, whose TC is lower than 5 Kelvin, for example. So the calculation of aluminum, the TC of aluminum is still an extreme challenge. And for this problem, so in our code, we use a uniform K mesh, but as is discussed by chairperson in this session, EPW uses very sophisticated interpolation techniques. So combining EPW and IR intermediate representation of the Green's function is an interesting project. And actually, Hiroshi Mori, my postdoc, is working very hard and tries to implement this technique in EPW. And actually, he is moving to the group of Roxana next month. And I hope that he will succeed in implementing this method in EPW. And I hope that the calculation of aluminum can be possible in the near future. And by the way, this technique can be used not only in Benito calculation, but also model calculation. For example, flex calculation for the multi-orbital Hubbard model. And so, yeah, this was done in collaboration with a group of Tim Behring. And so in this paper, we solved the obtained the TC of 3 orbital Hubbard model. So in the standard approaches, the numerical cost to solve the flex is quite high. So yeah, calculation for the temperature lower than 1 Kelvin, for example, is numerically very expensive. And about 20 years ago, together with Kazuhiko Kuroki, I proposed that maybe F-wave superconductivity is realized in sodium cobaltate. But at that time, so numerical cost to solve multi-orbital Hubbard model is very expensive. So we just calculate the eigenvalue of lambda, at high temperature. But if we use the techniques of intermediate representation of the Green's function, so here Nicholas, the student of Tim Belling, so he's calculated the eigenvalue at the temperature the order of 1 Kelvin. Okay, so this is the result for the ab initio Eliashberg calculation for LaH10. And in the original paper, we show the results of SCDFT and Eliashberg calculation. But here I'm showing only the result of Eliashberg equation because I want to focus on the result of Eliashberg. Yeah, SCDFT also gives a similar result. But we can see that the agreement between theory and experiment is quite nice. And for me, it seems that it's not an accidental coincidence. So quite a reasonable range of pressure. This symmetric structure, which is good for superconductivity, is realized, stabilized. And if we calculate TC, and then so it gives very close to the experimental value. And so, of course, I will not say too strong about that. We introduced a static approximation and our calculation based on the Migdal approximation. But still, this result is important and interesting. And it gives some suggestion to understand the superconductivity in the system. Okay, so 5 minutes. So, so in the next few slides, I would like to introduce our calculation for carbonaceous sulfur hydride. So in this case, in this paper, the authors claim that the group of Professor Diaz concluded that they observed the room temperature superconductivity. And but unfortunately, the crystal structure is not yet determined. So recently, so Jose Flores Rivas, so he did an extensive structure prediction calculation using the minima hopping method. And we found that in this convex hull, there are only not so many stable structures. And so actually A3S is very, very stable. And this is also, I think, a very interesting fact. So if we calculate thermodynamic instability, then the A3S is very stable. And if we introduce carbon, then the system becomes very unstable in general. And we found that only the structure around this H3S are thermodynamically stable. So we decided to study the effect of carbon doping in the H3S. And if we dope carbon, then the peak in the density of states becomes close to the Fermi level. So this is good for superconductivity. And if we solve the Eliashberg equation self-consistently, then so at 250 gigapascal, there is an enhancement of about 25 Kelvin. But it is not so big because if we plot the TC of this system, so this is the result for virtual crystal approximation, and this is the result for supercell calculation. And we see that these TCs are much lower than the values in the paper of Professor Diaz. So this is also an, I think, interesting result. And concerning the doping effect, we also study the effect of LaH10. So Jose again, so he introduced many kinds of elements in the networks of LaH10 Ab. And in many cases, the structure is destroyed. For example, if we put carbon, then immediately the cake is destroyed. But in the case of strontium or calcium, then the cake still survives. And if we calculate density of state, then, for example, in the case of calcium, the peak becomes close to the film level. And if we calculate TC, then again, we found enhancement of TC about 30 Kelvin. So this is calculation of 300 gigapascal. But if we have an enhancement of TC also in the about 150 gigapascal, then we can have a room temperature superconductivity. Okay, so let me conclude. So in the first part, I discussed the crystal structure of the system. So, and we found that both zero temperature, quantum effect and temperature effect are important to stabilize and the symmetric structure. And for TC calculation, we found that non-empirical self-conscious Migdal Eliashberg calculation gives a reasonable value for LaH10 Ab and also H3S. And maybe by doping, maybe we can enhance the TC. So these are the results of the calculation of TC. Okay, so thank you very much for your attention.